So let's look at some of the partial differential equations. We'll look in this chapter, introduction. So we will look at, so partial differential equations will be abbreviated as PDE. So we'll look at PDEs of the form a d square phi dx square plus b d square phi dx dy plus c t square phi dy square. And then there's more terms involving x, y, phi, d phi dx, d phi dy, all is equal to 0. Okay, so we'll only look at, so to say, second order partial differential equations because they model some of the phenomenon which we might have learned in other chapters, like fluid mechanics. Thermofluids typically have a PDE. Solid mechanics also has some PDEs. If you take finite element analysis, you'll see PDEs. So we'll classify this. So there's a classification of second order PDEs based on the values of A, B, and C. So if B square minus 4AC, okay, now A, B, C are clearly constants, is less than 0, this is known as a elliptic PDE. If B square minus 4AC equals 0, then this is a parabolic PDE. If P square minus 4AC is greater than 0, this is a hyperbolic PDE. Okay, so these different types of PDEs are classified based on the sign of that quantity, B square minus 4AC. Again, we'll look at some of these. Well, we'll look at examples of each of these in this chapter. This chapter is not on exam, correct? This chapter is not in exam 3, that is correct. This chapter is not in the exam on October 30th. Okay, so let's look at some of the examples. Okay, heat conduction equation. Okay, the example of a heat conduction equation is alpha t square t dx square equals dt t time. So we have to classify if it's a PDE or what type of PDE it is. So here B is, well, you can look at B is basically the coefficient of dx dy. C and A are the coefficients of the square term dx square dy square. So similarly, we can see that here B, which involves dx, in this case the other variable t, that term will be 0. A would be alpha and C would be 0. So B square minus 4AC will be 0. So this is a parabolic PDE. So that's one thing. That's the first thing we can infer. The second thing, and this is probably goes back to our ODEs, when we're given an equation like this involving second order, first order derivatives, we need to figure out the number of initial conditions you need to solve this. In this case, you need one initial condition. Okay, and that is due to d tau dt, right? Because you have dy dx sort of term, and you need, since this is a second order term in x, you need at least two boundary conditions, and the boundary conditions are typically only true for spatial, right? X is denotes something related to space, t is time. This is usually conduction in a rod, x0 x equals L, and the temperature profile of this rod is something we need to figure out. So that would be two boundary conditions, and those happen due to the term d square t dx square. So second order term, you need two boundary conditions. Okay, another example is Poisson's equation. Which goes as d square phi dx square t square phi dy square equals beta xy, some function of x and y. Okay, this occurs in actually occurs in electricity. So in this case, we can also figure out what ABC is. B is whatever is in front of d square phi by dx square, that's 1. Sorry, my bad. A is 1. A is whatever is in front of d square phi dx square. C is what is in front of d square by phi by dy square, and P is what is in front of the mixed term dx dy. So A is 1, B is C is 1, and B, which is the middle term, is not there, so it's 0. Okay, so we can say that V square minus 4AC is equal to minus 4, right? So that would make it an elliptic PDE. Okay, and it will need four boundary conditions. It will be two boundary conditions due to d square phi dx square, and two boundary conditions due to d square phi dy square. So four conditions are needed. And those, when I say boundary conditions, they can be anything like phi of x, phi of y, d phi dx, d phi dy, any combination of those. Okay, one more, and we'll look at one more equation. So the last one is the wave equation. Poisson's heat conduction. Look at the wave equation. See, this one looks like this. D square P d t square minus c square d square phi dx square equals 0. Okay, here B, let's say that B is the coefficient. Let's put A first. A is the coefficient in front of one of them. So let's just say it's before d square phi dt square. C is the coefficient before the other term, C, so it'll be minus c square. And then B is the term which is cross coupling, which is 0. So we can see that B square minus 4AC equals, so 0 minus, there's a minus here, so it'll be 4C square, but C is, whatever the value of C is, 4C square has to be positive. That's a square. So this term is greater than 0, so it's a hyperbolic equation. Okay. And so T here is time, so what we need here is two initial conditions due to d square phi dt square, and then two boundary conditions due to t square phi dx square.